Imagine, every day in kitchens across America, chicken pieces weighing 3 to 5 ounces are transformed into crispy legends. This ritual starts with 11 secret herbs and spices, hot oil sizzling at 350 degrees, and a piece of chicken plunged into it with a sound that makes your heart beat faster. History, flavor, and technology all come together in one bucket. Somewhere in the distant 1930s, in a forgotten mountainous area of Kentucky, Harland Sanders, an ordinary man with a restless character, stood at his small gas station cooking food for hungry drivers. He didn't have a restaurant, a chef's title, or a lot of money. He only had a slice of ambition, a handful of spices, and a fierce belief in flavor. When customers started coming not for gasoline, but for chicken, Sanders realized he had created something special. His secret? A blend of 11 herbs and spices that he kept in his head, never wrote down, and mixed by hand. The chicken was fried in pressure cookers, which preserved the meat's juiciness while delivering that very crunch everyone was looking for. In 1936, the state of Kentucky awarded him the honorary title of Colonel. Kentucky Colonel. Thus, the image that would become timeless was born. Colonel Sanders in a white suit with a mustache and southern charm. But the real breakthrough came in 1952. Sanders, already over 60, began traveling across America with his skillet, offering restaurants to cook chicken using his recipe in exchange for a percentage of sales. It was a revolution. He launched a franchise when no one even knew the word. By 1960, KFC was already everywhere. The white suit became a symbol, and the chicken, a legend. The company sold millions of portions, and the Colonel himself, although he later sold the business, remained its face and soul until his final days. His figure still stands on every logo, on buckets and packaging. Thus, a simple man from a gas station turned into the Chicken King, and his recipe into one of the most famous gastronomic secrets in the world. Today, production begins far from the city, on specialized farms where broilers are raised, chickens that grow to 4 or 6 pounds in 6 or 8 weeks. Here, everything is precise. Temperature, feed, water, lighting, all controlled by automation. The chickens don't roam the fields, but they grow uniformly without stress, which means the meat is soft, tender, without any tough surprises. When the time comes, climate-controlled trucks pick up a batch. Each truck maintains an optimal 40 degrees Fahrenheit to preserve freshness. The chickens are delivered to a processing plant where everything is automated to the level of science fiction. Just imagine, yesterday these chickens were running around a farm in Georgia or Tennessee, warming themselves under lamps and pecking at feed. And today, they are in a giant processing center. Huge trucks with the inscription, "Fresh Poultry Only," drive up to a sterile unloading dock, where the chickens enter a closed cold conveyor. The temperature in the receiving area is 34 degrees. Everything hums, flashes, spins, and workers in white coats, caps, and with a disinfectant spray on their belts are like cowboys with antiseptics. After processing on the primary line, stunning and slaughter, which are carried out automatically, instantly, and painlessly, the carcasses go to the defeathering machine. It's something between a washing machine and a centrifuge. Dozens of rotating rubber fingers gently but effectively remove all feathers in a matter of seconds. Next, internal processing. The chickens pass through a series of blades and nozzles that cut, clean, and wash, all automatically, under the constant control of sensors and cameras. Not a single drop of blood or remnant of entrails goes unnoticed. Infrared sensors detect even microscopic defects. The carcasses are washed, cooled in ice water or a spray shower, and sent on for portioning. Now pay attention, the chicken is never cut by eye. It's scanned, the thickness of bones and muscles is measured, and only then do special automated machines cut it into perfect parts. Thighs, drumsticks, breasts, wings, fillets. Everything, according to a KFC template, approved for every restaurant in the world. For example, a fillet piece should not exceed 3.5 ounces, and a drumstick should be no shorter than 6 inches. Did you know that? Each piece, by weight, volume, shape, is checked a second time. Those that don't quite meet the standards are not thrown away. They are sent to other chains, or for processing into cutlets, sausages, or even dog food. The next zone is quality control, which resembles an airport. Lab technicians in masks take samples, select pieces, weigh them, and enter them into a database. One mistake, and the entire batch goes into quarantine. Because food safety control never sleeps and never forgives. Then, the most important part, cooling and packaging. Here, the meat is placed in airtight trays, vacuum sealed or wrapped in film, and an identification barcode, batch number, processing time, branch name, and even the number of the truck that will transport the meat to the restaurant are added. All of this goes into refrigerated chambers, where it is stored at a stable 34 degrees until shipment. These chambers are like safes, automatic humidity and temperature control, limited access. Even the air is filtered to operating room standards. And so, a truck branded with the familiar red and white KFC logo carries this entire chicken symphony to the kitchens, where fryers, spices, employees, and buckets with happy faces are already waiting for it. The truck opens its back doors, and from it, as if under guard, trays of fresh, chilled chicken meat are unloaded. The temperature, as it should be, is no higher than 36 degrees. The kitchen team immediately receives the batch, checks the barcodes, and records it in the system, because every part, every drumstick is accounted for, like a soldier in battle. And then, the ritual begins. Before breading, each piece is checked by hand for any damage, excess fat, or cracks. Then the chicken is dipped in cold water so the breading sticks better. This isn't just a wet dip. It's preparation for a real crusade in the fryer. And here it is, the legendary flour mixture with 11 herbs and spices. Yes, that's the one. Only a few people in the world know the exact composition, and it's guarded better than a nuclear code. The mixture is stored in an airtight container, unloaded into a metal basin, and here the shaking begins. The chicken is tossed in the flour, then it's turned over 13 times by hand. Yes, not 12, not 14, but exactly 13. This is a sacred KFC number, a guarantee of even coating. The employees' hands move rhythmically, automatically, as in a combat dance. Everything must be tight, well coated, but without clumps. Next, the fryer. A fryer isn't just a pot of oil. It's an industrial war machine that maintains a precise temperature, 350 degrees Fahrenheit. It's a hell, so that you can later feel like you're in paradise. The pieces are carefully placed in mesh baskets and submerged. Immediately, SSS, the music of sizzling begins. The oil surrounds each piece from all sides. And now what's important, the chicken doesn't just float in the fat forever. It's fried on a timer, on average for 13 minutes, depending on the part. And what's next? The chicken doesn't go straight to the tray. It's placed on special racks to drain off excess oil. Then, into holding cabinets with heating, where it waits for its moment of glory for no more than 60 minutes. If it's not eaten, it's disposed of. Everything is fresh, without compromise. While the cashier is taking an order, the cook assembles the meal. A few crispy pieces, sauce, fries, a biscuit, and everything into a familiar white and red bucket or box. And then, onto a tray, into hands, into a car, into the heart. And there it is, the crunch, the very same one, legendary. It was born from precision, temperature, secrecy, and ritual. You can't fake it. You can't replicate it at home. Well, unless you try very hard. Because KFC isn't just chicken. It's an industry with the taste of childhood, road trips, first paychecks, and late-night snacks. Every day at factories operating under the KFC brand, over 1.5 million chickens are processed. Yes, that's right, 1,500,000 daily. That's about 17 birds every second while you were listening to this sentence. In a year, that's over 500 million. A chicken battalion that could occupy an entire state. On one portioning line, 150 chickens per minute. The machines don't sleep, the knives don't stop. Each fillet is cut with precision down to 1/10 of an ounce, goes into a vacuum package, is barcoded, and flies to a restaurant that could be 3,000 miles away. Even more interesting, more than 70% of the chickens that KFC sells in the US come from local farms, often family-owned. And every restaurant in the world, and there are almost 28,000 of them in 150 countries, has a standardized taste, verified by a laboratory.
A machine capable of squeezing metal like it's alive, not melting it, not breaking it, but forcing it to flow under pressure that's impossible to imagine. 80,000 tons of force concentrated at a single point. That's more than the weight of an entire army of tanks stacked on top of each other. But why does humanity need such inhumane power? And why is this giant hidden deep underground, as if they're deliberately trying to keep it out of sight? Under this press, they're not just making metal parts, they're forming the heart of airplanes, rockets, and reactors without a single welded seam. But there's one fact almost never discussed publicly. If you watch till the end, you'll understand why this press isn't an engineering marvel, but a tool of global dominance. How much is 80,000 tons? Just to put that in perspective, that's the equivalent weight of 80,000 cars compressed into a single point, or the pressure created by an entire army of giant elephants stacked on top of each other. This metal colossus, installed in 2013, is the world's most powerful forging press, surpassing all previous achievements. It's a true giant, reaching the height of a 10-story building. Its foundation is buried deep in the ground, while its upper section rises into the sky like an industrial skyscraper. It looks like a machine from a science fiction movie, but it's absolutely real and performs its incredible work every single day. This press is designed for stamping extraordinarily large and complex parts that are critically important for the aviation, aerospace, and energy industries. These can be massive panels for rocket bodies, huge wing or fuselage components for aircraft, turbine parts for power plants, or even reactor equipment. The story of these giant presses is its own epic saga, deeply intertwined with the Cold War era. Back when the USA and USSR were competing for dominance in the space race and military industry, there arose a need for super strong, seamless metal structures. The Americans were first to build presses with a capacity of 50,000 tons, allowing them to create large aircraft components without welds, drastically improving reliability. The Soviet Union wasted no time responding, creating an even more powerful 75,000-ton press that also became a legend of engineering ingenuity. These titans of their time represented the pinnacle of metallurgical technology, symbols of engineering superiority and the industrial might of superpowers. They were true monsters, capable of shaping metal with such force it seemed almost impossible. But this modern Chinese press shattered all those records, surpassing even the Soviet giant. It can crush metal with literally superhuman force. Under this press, red-hot metal blanks weighing hundreds of tons, that's like dozens of trucks compressed into a single chunk of metal, get flattened like soft clay. Metal heated to a red or yellow glow undergoes incredible pressure. It doesn't just deform, it flows under this colossal force, slowly but relentlessly taking on the required pre-designed shape. This isn't casting, this is forging, a process that strengthens the metal structure, making it denser and stronger than any cast piece. This ability to produce solid forgings of enormous size is the main advantage and defining characteristic of such presses. Picture this. You can get a massive spar for an aircraft wing or a reactor vessel component without a single weld.
Weld seams, no matter how high quality they are, will always be potential weak points in metal structures. They can be sites of stress concentration, cracks, or corrosion. In mission-critical components, where the cost of failure can be catastrophic, say in an aircraft at 33,000 feet, or in a space rocket, the absence of weld seams isn't just desirable, it's absolutely essential. Solid forgings, formed under such pressure, have unmatched strength, uniform structure, and maximum reliability. They're the foundation for building supersonic aircraft, ultra-powerful rockets, spacecraft, and safe nuclear reactors. To install a press of this magnitude, you don't just build a foundation, you build an entire underground iceberg. The main structure of the press is buried deep in the earth because the enormous forces acting during forging create incredible vibrations that need to be absorbed. It's like building a foundation for a skyscraper, but in reverse, plunging into the depths of the earth for dozens of feet.
Installing equipment like this is a more complex logistical operation than launching a space rocket. Press components arrive on site by the hundreds, then get assembled using giant cranes and engineering teams working for years. By the way, an 80,000-ton press force isn't just pressure, it's a controlled transformation of material at the micro level. Under that kind of force, the metal's crystalline structure changes. Grains become finer and denser, giving it exceptional mechanical properties. It's like leveling up metal to maximum stats. Here's another thing. Running a giant like this takes a colossal amount of energy. This isn't just plug it into an outlet. Powering the hydraulic pumps and maintaining stable pressure requires a dedicated power plant.
And the cooling systems that carry heat away from the hydraulic fluid, just as critical. Under these loads, the oil can get seriously hot. It's a true engineering ecosystem where every single component is mission critical for the entire complex to function. As we mentioned, instead of welding together dozens of small metal sheets, the press can forge a significant portion of the shell from a single block of metal. This makes the structure lighter, stronger, and far more resistant to fatigue. While the press doesn't stamp out tiny turbine blades, it can form large casing components for jet engines, parts that withstand extreme pressure and temperature.
Beyond aerospace, where every single pound and every hairline crack can spell disaster, this press also stamps out components for nuclear and thermal power plants. We're talking ultra-high-strength reactor housings and lids, turbine elements, generators, and other equipment operating under extreme pressure, temperature, and radiation. Here, integrity and zero defects aren't just about efficiency, they're about protecting entire regions. They also forge shafts and rotors for massive ships and industrial machinery. Enormous turbine installations on ocean-going vessels or in power generation require ultra-strong shafts that can handle colossal rotational forces and torsional loads. Forgings made under this press are perfectly suited for these purposes.
Imagine a cruise ship taller than 15-story building, longer than 3 football fields, weighing 70,000 tons. Now imagine driving at full speed onto a beach. That's how ships die. Every year, over 700 ocean giants make their final voyage, not to ports, but to demolition beaches in Bangladesh, India, and Pakistan. Workers with blowtorches dismantle these steel leviathans piece by piece, standing where waves meet rust. How does a vessel carrying 3,000 passengers become rebar for apartment buildings? What happens to the swimming pools, the engine rooms, the miles of copper wiring? Stay with us. You'll discover the brutal, beautiful process transforming floating cities into raw materials, and the shocking secret of why 95% of every ship lives again in different form. Our journey begins in Chittagong, Bangladesh, the world's largest ship-breaking beach. The coastline stretches 8 miles, littered with steel carcasses in various stages of dismemberment. From satellite view, it resembles a graveyard of metal whales beached in neat rows. Up close, it's controlled chaos. 15,000 workers crawling over hulls like ants dismantling elephants. The tide determines everything here. Ships arrive during spring tides when water rises highest. Captains gun engines to maximum, driving vessels onto mudflats at 15 knots. The impact shudders through steel bones. When tide retreats, the ship sits stranded, a beached giant awaiting dissection. Workers call this beaching. International shipping calls it the end. Before any cutting begins, the ship must be cleared. Imagine walking through abandoned cruise liner. Swimming pools drained, casinos silent, 3,000 cabins empty. Everything removable gets stripped. Furniture sold to local markets, lifeboats auctioned to fishing villages, artwork shipped to collectors worldwide. The chandelier from the grand ballroom? Now hanging in a Dhaka restaurant. Hazardous materials require special handling. Asbestos insulation wrapped every pipe in ships built before 1990. Workers in basic masks, far below Western safety standards, remove it by hand. Oil residue coats engine rooms inches thick. Fuel tanks supposedly emptied still contain deadly vapors. Last year, 17 workers died in Bangladesh yards from explosions and toxic exposure. This is dangerous work done by desperate men. The cutting begins at the bow. Workers climb scaffolding made from ship parts, wielding oxyacetylene torches, burning at 6,000 degrees. Steel glows cherry red, then separates. Chunks weighing tons crash onto beach sand. Shaking ground felt hundreds of yards away. Watch the cutter teams. They work in pairs. One torches, one watches for falling debris. No hard hats. Flip-flops instead of steel-toed boots. Yet their precision is remarkable. They know exactly where to cut, following structural blueprints memorized through years of experience. The ship tells you where it wants to break, says one veteran. Fight the steel wins. Work with it, you go home alive. As the superstructure disappears, the real treasure emerges, the hull. This is where serious tonnage lives. Hull plates measure 1 inch thick, weighing hundreds of pounds per square foot. Cranes, themselves salvaged from previous ships, lift cut sections onto flatbed trucks. The steel heads to re-rolling mills within miles of the beach. Picture the economics. A scrapped container ship sells for $500 per ton. 60,000 tons equals $30 million, split between ship owner, yard owner, and workers earning $3 daily. The math seems cruel, but it's why these yards exist. No Western facility can compete with labor costs. Environmental regulations alone would triple expenses. The engine room reveals industrial archaeology. Marine diesels the size of houses, 12 cylinders, each taller than a man, get disassembled bolt by bolt. These engines ran continuously for 30 years, burning heavy fuel oil thicker than honey. The engineering is magnificent. Crankshafts weighing 50 tons, precisely balanced to spin at 100 RPM without vibration. This machinery doesn't get melted. It gets resold. Ship engines power factories across South Asia. Generators light villages without grid connections. Pumps irrigate farms. The secondary market for marine equipment employs thousands of traders, mechanics, and transporters. Nothing from a ship truly dies. It migrates into developing economies, extending useful life decades beyond original purpose. Below the waterline lies the double bottom, the ship's structural spine. These compartments held ballast water, fuel reserves, sometimes cargo. Accessing them requires cutting through multiple steel layers, descending into spaces never designed for human comfort. Workers joke darkly about the belly, where heat concentrates, air thins, and escape routes disappear. Cutting the double bottom takes weeks. Each section weighs tons, but must be removed carefully. Collapse here buries workers under steel avalanches. Supervisors watch from shore, tracking progress through radio calls. When sections finally break free, cranes swing them clear while workers scatter. The beach cheers each successful lift. These small victories accumulate into complete demolition over months. The propeller comes last and commands highest prices. Bronze propellers weighing 40 tons contain copper, aluminum, nickel, and manganese in precise alloy. Scrap value exceeds $200,000. Yards guard propellers like treasure, storing them in secured compounds until specialty metal dealers arrive. Watch the propeller removal. It requires precision cutting around the shaft, then carefully lowering the massive bronze flower onto reinforced trailers. One slip damages blades worth thousands each. The journey from beach to foundry happens under armed guard. Bronze theft funds criminal operations throughout the region. When finally melted, this propeller might become electrical wiring, plumbing fixtures, or musical instruments. The ship's heartbeat transforms into civilization's nervous system. Shipbreaking emerged from necessity after World War II. Hundreds of Liberty ships, hastily built for wartime cargo, became obsolete overnight. Scrapping them created the modern industry. Taiwan dominated through the 70s, then Korea, then China. Environmental regulations pushed the trade to South Asia by the 90s. Chittagong rose because geography cooperated. Extreme tidal ranges, 16 feet between high and low, create natural dry docks. Sandy beaches cushion impacts. Cheap labor, minimal regulation, and proximity to steel-hungry construction markets completed the equation. Today, Bangladesh breaks 40% of global tonnage. The industry employs over 200,000 workers directly, plus countless more in supporting trades. Love it or hate it, shipbreaking built modern Bangladesh. Carbon emissions drop 62% using ship-sourced steel versus virgin ore production. Industry recycles 20 million tons of steel annually, enough to build 4,000 skyscrapers. A single aircraft carrier yields enough metal for 15 apartment towers housing 50,000 people. Here's the secret we promised. That ship doesn't just get recycled, it gets reincarnated completely. 95% of every vessel finds new life. Steel becomes rebar reinforcing buildings throughout Asia. Copper wiring powers homes. Furniture furnishes restaurants. Lifeboats become fishing vessels. Even the wooden decking becomes flooring in European boutiques, marketed as reclaimed teak at premium prices. From ocean voyager to urban infrastructure, the transformation completes. We've built an ecosystem where nothing truly disappears. That cruise ship where honeymooners danced might now support the hospital where their grandchildren are born. The container ship carrying your television might become the bridge you drive across. Ships don't die on those beaches. They scatter into civilization, becoming the hidden skeleton of modern life. Steel ghosts supporting everything we build.
Without nickel, Tesla's electric vehicles wouldn't exist. Every year, over 3 million tons of this silvery metal get extracted from Earth's crust. 70% destined for stainless steel, 30% powering the battery revolution transforming transportation. Picture this. Inside every electric car battery, nickel accounts for up to 80% of cathode weight, storing the electrical energy making 500-mile ranges possible. How does rock buried 2 miles underground become the metal enabling carbon-free futures? How do ancient asteroid impacts create deposits worth billions? Stick around till the end. You'll discover why this metal, discovered in 1751, became overnight the most critical resource for climate solutions, and the shocking environmental price we pay for every kilowatt-hour stored. The story begins in Sudbury, Canada, ground zero for one of Earth's largest meteorite impacts. 2 billion years ago, a 6-mile-wide asteroid slammed into primordial crust with force equaling 6 billion Hiroshima bombs. That cataclysmic collision melted rock 60 miles deep, concentrating nickel-rich magma into deposits mining companies extract today. Standing at crater's edge feels like visiting Earth's wound that never healed. Modern mining descends through vertical shafts, plunging 7,000 feet, deeper than 6 Empire State Buildings stacked vertically. Massive cage elevators, traveling at speeds exceeding 30 miles per hour, drop miners into darkness in under 4 minutes. That's falling through bedrock older than complex life itself. Underground, temperatures reach 120 degrees Fahrenheit from Earth's geothermal heat, requiring industrial air conditioning, pumping cold air through 40-mile tunnel networks. Next comes extraction, where explosive specialists drill blast holes following nickel-bearing veins. Charges containing ammonium nitrate, industrial explosive used in quantities measured by tons, fracture solid rock with controlled violence. The deafening thunder from underground blasts shakes surface buildings miles away, rattling windows in synchronized waves every afternoon at precisely 4 o'clock shift change. Giant load haul dump machines, nicknamed LHDs and standing tall as double-decker buses, scoop 50 tons per bucket. Picture mechanical mastodons navigating tunnels barely wider than their frames. Operating in perpetual darkness illuminated only by headlamps, drivers maneuver 60-ton machines through labyrinths where wrong turns mean hours backtracking. Every shift, these machines transport 15,000 tons of ore, weight equivalent to 75 blue whales, through underground highways to crushing stations. Surface processing begins where jaw crushers, standing 4 stories tall with opening widths matching garage doors, pulverize boulders into gravel-sized chunks. With bone-rattling vibrations felt through steel-toed boots, hydraulic jaws generate crushing forces exceeding 15,000 pounds per square inch. Operators monitor crack propagation. Rocks splitting wrong create jams requiring dangerous manual intervention with jackhammers. Conveyor systems stretching 8 miles, longer than Central Park, transport crushed ore to grinding mills. Inside rotating drums 30 feet in diameter, 25-ton steel rods tumble with ore, creating grinding cacophony resembling continuous thunder. Processing 12,000 tons hourly, that's loading freight trains non-stop. This powder, finer than beach sand, flows to flotation cells, where chemicals separate nickel sulfides from waste rock using bubble physics. Nickel concentrate emerges containing 20% metal, ready for the real challenge: purification. Next comes roasting, a pyrometallurgical inferno where concentrate gets heated in massive kilns to 1,400 degrees Fahrenheit. At these temperatures, sulfur burns away as sulfur dioxide, leaving behind nickel oxide mixed with iron. Picture industrial-scale barbecuing where the meat is rock and smoke contains compounds requiring scrubbing before atmospheric release. The roasted material, now crumbly and porous like volcanic pumice, moves to smelting furnaces, where temperatures climb to 2,600 degrees Fahrenheit. Electric arc furnaces, consuming power equivalent to small cities, enough electricity to run 12,000 homes, melt oxide into liquid matte. This molten mixture, containing 60% nickel and 40% other metals, glows white-hot like captured starlight. Every 2 hours, furnaces tap this liquid fire into ladles holding 200 tons. The purification process intensifies with converting, where oxygen blasted through molten matte at supersonic speeds burns away remaining sulfur and iron. Massive Peirce-Smith converters, rotating horizontal cylinders 40 feet long, operate like blast furnaces lying sideways. Inside these rotating drums, chemical warfare occurs. Oxygen attacking sulfur bonds, creating temperatures hot enough to vaporize copper. This step is critical because timing determines purity. Blow too long, nickel oxidizes wastefully. Too short, impurities contaminate final product. Operators monitor color changes in flames shooting from converter mouths. Blue flames mean sulfur burning, yellow indicates iron removal, clear white signals nickel ready. That visual chemistry, unchanged for centuries, guides decisions affecting millions in product value. After converting, nickel matte achieves 78% purity, but battery manufacturers demand 99.9%. After converting, the real magic begins, electro-refining. Here, physics and chemistry converge in massive electrode halls housing thousands of cells. Impure nickel anodes, cast into plates weighing 300 pounds each, suspend in electrolyte baths containing nickel sulfate and sulfuric acid. Electric current flowing through these baths, think industrial-scale electroplating, dissolves nickel atoms from anodes, transporting them through liquid to deposit on pure nickel starter cathodes. Picture this: over 10 days, nickel migrates atom by atom across 6-inch gaps. Impurities like cobalt, copper, iron stay behind, falling as sludge to cell bottoms. This sludge, later processed separately, contains precious metals including platinum, gold, palladium, making waste worth more than many ores. Temperature control matters critically. Too hot, dendrites form, metal crystals bridging electrodes causing shorts. Too cold, deposition slows uneconomically. Electrorefining requires surgical precision in industrial setting. Computer systems monitor voltage, amperage, temperature across 15,000 individual cells simultaneously. Operators adjust current by milliamps. Modern refineries achieve nickel purity of 99.99%, only one impurity atom per 10,000. That's purity rivaling semiconductor-grade silicon. After 10 days, workers crane lift finished cathodes, now coated with 400-pound nickel deposits from baths. Mechanical strippers peel nickel from starter sheets like removing wallpaper. These pure nickel sheets, called cathodes, get melted into pellets for battery manufacturers, or alloyed with chromium and iron for stainless steel. The energy intensity staggers. Producing 1 ton of battery-grade nickel consumes 50 megawatt-hours, enough electricity to power average American homes for 60 days. This industry transformed radically in 15 years. Back in 2010, nickel prices averaged $7 per pound, used primarily for stainless steel. Battery applications consumed less than 5% of global production. That all changed when Elon Musk's Master Plan 2 announced Tesla's battery gigafactories in 2016. The breakthrough came when battery chemistry shifted from cobalt-heavy NCAs to nickel-rich NCMs, nickel, cobalt, manganese cathodes containing 80% nickel. Suddenly, every electric vehicle needed 110 pounds of nickel. Global demand exploded. Prices spiked to $9 per pound by 2022. Indonesia, containing 21% of world's reserves, transformed from minor player to dominant producer. Today, battery applications consume 43% of new nickel production. By 2035, International Energy Agency projects batteries will consume 75%, driven by 200 million electric vehicles requiring 23 million tons cumulatively. Carbon emissions drop by 18% when recycling nickel versus mining virgin ore, equivalent to removing 3 million cars annually. Industry saves over $22 billion yearly through recycling. Processing costs drop 31% because smelting scrap requires half the energy of complete ore processing. So here's the secret promised. Nickel is humanity's transition metal, literally bridging fossil fuel era to electric future. But here's the dark truth. Extracting nickel for just one EV battery produces 8 tons of CO2 emissions. That electric car carries invisible environmental debt, requiring 35,000 miles of driving before breaking even with efficient gasoline vehicles. The green revolution isn't free. It's an energy trade-off where extraction today enables emission reductions tomorrow. From asteroid impacts to electric highways, cycle completes. We're mining ancient cosmic collisions to power climate solutions. Nickel doesn't solve pollution, it relocates it, concentrates it, transforms it into manageable problem. That's not failure, that's engineering reality. Every solution creates new challenges. The question isn't whether mining nickel harms Earth, it does. The question is whether preventing catastrophic climate change justifies temporary scars.
Every year, the world melts over 1 billion tons of pig iron. But where does all that fiery metal come from? Imagine a giant furnace as tall as a 35-story skyscraper that never sleeps. Its guts glow like the Earth's core, and the temperature hits 3,600 degrees Fahrenheit. That's 2,000 Celsius. This is a blast furnace. They don't just melt metal here. They give birth to the heart of industry. But there's a secret that only the guys standing at the tap hole know. If you stick around to the end, you'll find out what's really happening in the center of this burning fortress and why it changes everything. Imagine a colossal tower, taller than a 35-story skyscraper. The ground beneath your feet vibrates slightly from its relentless work, and the air is filled with a hum, like the breathing of a giant beast. At night, its top glows, pushing back the darkness. This is a blast furnace, a massive vertical smelter where 24 hours a day, 7 days a week, the magic of turning ore into metal happens non-stop. Why blast furnace? The name comes from the process itself, and it's no accident. The whole secret to a blast furnace is the constant blast of incredibly hot air that fuels the fire and kicks off all the necessary reactions. If you were to slice a blast furnace open, you'd see it looks like a stretched out bottle. Every part of it has a name and a purpose. The walls of the furnace are lined with special refractory bricks, capable of withstanding temperatures that would melt solid rock. This is a true fortress, built to tame fire itself. So what do they feed into this fiery throat? The process is like cooking from a very strict recipe. The mix of ingredients loaded into the furnace is called the charge. Here are its main components: iron ore, fuel, coke, and fluxes. These three ingredients are loaded into the furnace in precisely measured layers. A layer of coke, then a layer of ore with fluxes, then coke again, and so on. Every few minutes, a new batch weighing tens of tons is sent into the furnace. The iron ore is the foundation of it all. They usually don't just use raw ore dug from the ground, but specially prepared sinter or pellets. These are baked clumps of fine ore, or rolled balls of ore concentrate. The main goal is to have as much iron oxide in the raw material as possible, from which the oxygen will later be ripped out. Coke is coal that's been cooked in special ovens without access to air. After this treatment, it becomes strong, porous, and burns with an immense amount of heat. But that's not its only role. The carbon that makes up coke is the real magician that turns ore into metal. The flux is most often ordinary limestone. Why is it needed? The ore and coke always have useless impurities, so-called gangue. The limestone helps to bind these impurities, forming an easily meltable slag. So, the charge is loaded. What's next? This is where it gets interesting. Two streams move towards each other. From the top, the layers of the charge slowly descend, and from the bottom, a hurricane of superheated gases rushes up to meet them. It all starts at the bottom, in the hearth. Through special pipes called tuyères, air heated to a scorching 2,200 degrees. Fahrenheit, 1 to 200 Celsius, is blasted into the furnace under huge pressure. That's hotter than volcanic lava. Meeting the red-hot coke, the oxygen in the air instantly ignites. The temperature in this zone skyrockets to 3,600 degrees Fahrenheit, 2,000 Celsius. This creates carbon dioxide. But as it rises higher and passes through new layers of coke, it turns into another gas, carbon monoxide. And this gas is the real oxygen thief. As this searing hot stream of gas rises up the furnace shaft, it envelops the chunks of ore and begins to greedily rip the oxygen from them, leaving behind reduced, spongy iron. The reduced iron continues its journey downward into hotter and hotter zones. It passes through the glowing layers of coke and, like a sponge, begins to soak up its carbon. And here's where something amazing happens. Pure iron melts at a very high temperature of 2,800 degrees, 1,530 Celsius. But soaking up carbon dramatically lowers that melting point. That's why a blast furnace doesn't produce pure iron, but an alloy of iron and carbon, pig iron, which becomes liquid at just 2,200 degrees, 1,200 Roughly every 40 to 60 minutes, enough liquid products have collected in the bottom of the furnace. It's time for the climax, a truly mesmerizing sight. A furnace worker, the keeper, uses a special drill to punch open a hole in the furnace wall, the tap hole. First, they tap the slag. It's lighter than the iron, so it floats on top. It's a molten, lava-like mass that flows into special ladles. And then they open the iron tap hole, and a dazzling, sparking stream of molten metal erupts with a roar. This is the River of Fire. The temperature of this stream is around 2,700 degrees Fahrenheit, 1,500 Celsius. It flows down special troughs, bathing everything around in a blinding light, and fills giant ladles that look like railway tankers. Each of these ladles holds hundreds of tons of liquid metal. From here, the pig iron will be sent to its next stage, either poured into molds or, more often, sent for further processing into steel. A blast furnace is an amazing operation that produces more than just pig iron. The byproducts are just as important. The blast furnace slag, which we've already mentioned, becomes a valuable raw material for making cement, building blocks, and road aggregate after it's cooled and crushed. The blast furnace gas that comes out of the furnace isn't just released into the atmosphere. It's cleaned of dust and used as fuel to heat the very same air that's blasted back into the furnace. It's a closed-loop system that makes the process more economical. Without a doubt, metallurgy is a serious challenge for the environment. However, modern technologies are constantly evolving. When blast furnaces are modernized, powerful filters and cleaning systems are installed to capture dust and harmful gases. Scientists and engineers around the world are working on creating green technologies, like using hydrogen instead of coke, to make metal production cleaner. But for now, the blast furnace remains the king of metallurgy. And every time you see a bridge, a skyscraper, or a train, remember these fiery giants and the people who tame rivers of fire to give the world a strong and reliable foundation. For 75 years, from the late 19th century to the 1970s, the USA was the undisputed world leader in the production of pig iron, steel, and rolled products. During this period, the American iron and steel industry wasn't just a sector of the economy, it was the key, or barometer, of the American economy. In the 1920s, for example, the country produced about half of the world's pig iron. Imagine that. Every other ton of this strategic metal in the world was born right here in American furnaces. Imagine this. Hidden right under your feet could be a mountain of old car tires. You'd think it's just rubbish, left to rot in a landfill for centuries. But what if I told you that this black rubber gets a second life and becomes the foundation for modern sports stadiums? Every single football field uses up to 40,000 tires. Now, multiply that by the more than 13,000 arenas in the US alone, and you get hundreds of millions of old treads, transformed from the road into a green carpet for athletes. How exactly new life is born from dirty scraps? We're about to break it down, step by step. Stick around till the end, and you'll uncover a secret most people never even thought to look for. So today, we're heading to a cemetery. A car tire cemetery. Acres of land piled high with mountains of black rubber rings. These are the silent veterans of the road, having done their thousands of miles, now lying here, seemingly useless. But this isn't the end of their story. It's just the beginning of their amazing reincarnation. We'll follow how these worn-out, dirty pieces of rubber go through a series of brutal, yet high-tech trials to be reborn as the soft, springy heart of a modern sports stadium. This is the story of how the roar of the road turns into the quiet whisper under an athlete's feet. Americans have learned to give a second life to the vast majority of tires. The recycling rate for old tires in the US is now over 85%. That's one of the highest rates for any consumer product. That means over 250 million tires a year dodge the landfill and are sent off for a new life. Some of them are burned as highly efficient fuel, some are used in civil engineering, but a significant and growing number are turned into that very same crumb rubber. In this tire cemetery, a machine that looks like a steel Tyrannosaurus Rex is at work. This is an industrial shredder. A huge loader grabs a whole handful of old tires and dumps them into the machine's steel jaws. Inside, two massive shafts with thick, sharp hooks spin with a deafening screech. They grab the tires with relentless force and, with an incredible crack, tear them to pieces. There's nothing delicate about it. The shredder's job is simply to break the tire's integrity, turning it into rough, palm-sized chunks. At this moment, the first important liberation occurs. Inside, every tire is a steel cord, a strong frame of steel wire. As the tire is torn apart, this cord is released, turning into a shiny web of steel threads mixed with rubber chunks. This chaotic mix of rubber and steel moves along a conveyor belt. And here, a powerful, massive industrial magnet spinning above the stream of shredded material comes into play. Like a fridge magnet, but 1,000,000 times stronger, it pulls all the steel threads from the rubber mass. With a screech and a clatter, the steel cord sticks to the magnet and is dropped into a separate container. This steel will later be sent off to be melted down, while our cleaned rubber continues its journey. But it's still too big and coarse. The next stop is the granulator. This is something like an angry coffee grinder the size of a car. Inside, sharp blades spin at enormous speed, chopping the large chunks into a smaller fraction, about the size of a fingernail. During this process, another component of the tire is released, the textile cord. These are nylon or polyester fibers that gave the tire extra strength. These light, fluffy fibers need to be removed. To do this, the rubber granules pass through a system of vibrating screens and air separators. Powerful streams of air literally blow away the light textile fluff, leaving only clean, heavy rubber granules. Now we have a clean, but still quite large material. To become the surface of a stadium, it needs to be turned into a crumb. For this, the granules are sent for final grinding, often in what are called cracker mills. These are two massive, grooved steel rollers that rotate towards each other at different speeds. The rubber granules, falling between them, are not so much cut as they are torn and ground into the tiniest particles. As a result of this process, we finally get what this was all about: crumb rubber. It's a uniform, free-flowing mass, like black caviar or coarse sand, where each particle is only a few millimeters in size. This crumb is carefully sifted to ensure a perfectly uniform size and is packed into huge 1-ton bags. Its journey from a dirty tire to a clean, high-tech raw material is complete. And now, let's jump to the place where this black crumb will find its true calling: the construction of a new stadium. Workers roll out huge rolls of artificial turf over a perfectly leveled gravel base. This isn't just a green carpet. It's a backing with long, soft polyethylene blades sticking straight up. But for now, they look sad and limp, pressed against the base. For them to stand up and look like real grass, they need support. And this is where a special machine, looking like a large fertilizer spreader, drives onto the field. A process called infill begins. First, the machine spreads a uniform layer of fine, rounded quartz sand over the entire field. It's heavy and settles right at the base of the carpet, acting as ballast to keep the turf from shifting and helping to stabilize the blades. And following the sand, our main hero is spread onto the field, the black crumb rubber. The machine distributes it just as evenly over the entire surface, and here, the main transformation happens. This crumb fills the space between the blades, forcing them to stand vertically, just like real grass. Secondly, and most importantly, it creates a cushioning layer. When an athlete runs, jumps, or falls, this layer of billions of tiny, springy rubber particles compresses, absorbing the impact energy. It's like running on a billion tiny trampolines. This drastically reduces the strain on athletes' joints and makes falls much safer. The final touch is combing the field. A special machine with a huge brush drives over the turf, thoroughly mixing the sand and crumb rubber and brushing them deep down to the base, making every blade stand perfectly straight. And so, when the work is done, what stands before us is a perfectly green, resilient, and safe field. And none of the players running on it might ever guess that under their feet, between the bright green blades, lie millions of particles of old car tires that have completed their epic journey from the roar of the motorway to the quiet, springy surface of a sports arena, having received a second, much nobler life. To create one standard American football or soccer field, you need, on average, between 20,000 to 40,000 old passenger car tires. Just think about it. A single field completely eats up a whole mountain of rubber waste. And how many of these fields are there in the country? Right now, there are over 13,000 artificial turf fields in the US, at schools, colleges, parks, and professional arenas. And that number is growing every year. Now for some simple maths, even if we take the minimum figure of 20,000 tires per field, it turns out that over 260 million old tires have found their new home in the surfaces of sports fields across the country. That's almost a year's supply of all the rubber scrap the country generates. Natural grass is a very fussy thing. It needs to be constantly mowed, watered, fertilized, and given time to rest. On average, a natural field can handle no more than 20 hours of play per week. And an artificial turf field? It can operate 24 hours a day, 7 days a week, in rain or shine. Now, let's talk about water. A single artificial turf field can save from 500,000 to 1 million gallons of water every year. That's the amount of water an average family uses in several years. Add to that the savings on fertilizers, pesticides, and lawnmower work, and the benefit becomes obvious. So next time you see a bright green field, know that it's not just a place to play. It's a monument to human ingenuity that solves a waste problem, makes sports safer, and saves precious natural resources, one old tread at a time. Imagine a metal that's lighter than steel, stronger than aluminium, and can withstand temperatures at which other materials simply burn up. A metal used to build aircraft that conquer space and implants that serve people for a lifetime. Sounds like science fiction? But this is titanium, one of the most mysterious metals on Earth. It starts with tiny grains of ilmenite and rutile and ends up as parts for supersonic jets and spacecraft. But few people know. Behind the gleam of titanium lies a manufacturing secret so dangerous and energy intensive that it's rarely spoken of. If you watch till the end, you'll learn something that will forever change your perception of this metal. The story of titanium production begins in the late 18th century when, in 1791, a British clergyman and amateur mineralogist named William Gregor discovered a new metal in the mineral ilmenite, which is now the main source of titanium. Initially, this metal was called menaconite, but later, in 1795, the German chemist Martin Klaproth rediscovered the element in the mineral rutile and named it titanium, in honor of the mythical Titans, giants of ancient Greek mythology. However, the pure metal was first successfully isolated only in 1825 by the Swedish chemist Berzelius, though at that time it was contaminated with impurities and practically unsuitable for industrial use. The first attempts at industrial production of titanium began only in the 20th century. In 1910, the American chemist Matthew Hunter obtained a small amount of pure titanium, and the real breakthrough came in 1925 when Dutch scientists Van Arkel and de Boer developed a method for producing high-purity titanium, paving the way for its widespread application. From the mid-20th century, titanium production developed intensively, especially in the USA, where the metal became indispensable in aviation, the space industry, and military applications. The production of titanium starts with the mining of titanium-bearing raw materials, mainly the minerals ilmenite and rutile, which contain titanium oxides. These ores are found in placer or lode deposits and are widespread across the globe, particularly in Australia, Canada, China, Norway, and South Africa. After mining, the ore undergoes a complex multi-stage processing. First, it is enriched, separating the titanium minerals from the waste rock to obtain ilmenite or rutile concentrates. Then, the concentrates are subjected to chlorination, which results in the formation of titanium tetrachloride, a volatile substance that is purified by distillation. This process allows for the removal of impurities and the production of a high-purity intermediate product. Next, the titanium tetrachloride is reduced with magnesium or sodium in special reactors at high temperatures in an inert atmosphere, producing titanium sponge, a porous metallic powder. This titanium sponge is then pressed, melted, and cast to obtain ingots or billets for further processing. The production of titanium is energy-intensive and expensive due to the complexity of the technological processes and the need to work in high-purity conditions. The main industrial method for producing titanium is the Kroll process, which remains the global standard. It involves the chlorination of titanium ore, purification of titanium tetrachloride, and its reduction with a metal, allowing for the production of high-quality metal for aviation, space technology, medicine, and other industries. Thus, titanium production begins with the mining of ilmenite and rutile, goes through complex chemical reactions and physical processing to transform natural minerals into a high-tech metal that combines lightness, strength, and corrosion resistance. The initial stages of titanium production are based on a complex, multi-step technological process that begins with the extraction and preparation of titanium-bearing raw materials, mainly ilmenite and rutile. These minerals contain titanium oxides, which must be converted into chemically pure titanium tetrachloride. To do this, the titanium ore concentrates are chlorinated in fluidized bed reactors at a temperature of 1,800 degrees Fahrenheit, where carbon and chlorine gas react with the raw material to form titanium and carbon monoxide. This tetrachloride contains impurities of other metals, which are removed by distillation to obtain high-purity technical titanium. The next key stage is the reduction of titanium tetrachloride to metallic titanium. The most common industrial method is the Kroll process, in which titanium tetrachloride reacts with magnesium in a vacuum chamber at high temperature. The result is titanium sponge, a porous metallic powder containing impurities of magnesium and magnesium chlorides. This reaction mass is subjected to vacuum distillation to remove impurities, after which the titanium sponge is pressed and remelted into solid ingots or slabs. The resulting titanium ingots are then used to produce alloys, rolled products, sheets, and complex parts. The entire process requires strict control of purity, temperature regimes, and safety, as titanium actively reacts with oxygen and nitrogen when heated. Just look at how incredible it is. A porous, light, and seemingly fluffy mass of metal. This is titanium sponge. It looks nothing like a regular metal bar, but more like a piece of metallic sponge or foam, only made of titanium. But this fluffy material is the first step towards creating strong and reliable titanium ingots, which are then used in aviation, medicine, and other high-tech industries. First and foremost, titanium ingots can be used to create titanium alloys, mixtures of titanium with other metals that enhance its properties. To obtain an alloy, alloying elements are added to the molten titanium, most often aluminium, vanadium, molybdenum, iron, or niobium. These additives change the metal's structure, increasing its strength, heat resistance, corrosion resistance, and improving its workability. The production of alloys usually takes place in vacuum arc furnaces, where the metal is melted at high temperatures in a protective atmosphere to avoid oxidation. To achieve a homogeneous composition, the alloy is remelted several times, after which it is cooled and prepared for further processing. The next stage is rolling. Ingots or slabs of titanium and titanium alloys are heated to a certain temperature to make the metal more malleable and are passed through special rollers. Rolling allows for reducing the metal's thickness, giving it the desired shape and size, as well as improving its structure and mechanical properties. The result is various types of rolled products: strips, ribbons, wire, and bars. Rolling can be hot or cold, depending on the requirements for the final product. From these rolled products, sheet metal is made: thin, flat blanks that are widely used in construction, aviation, medicine, and other industries. Titanium sheets are distinguished by their high strength and corrosion resistance, and are also easily subjected to further processing, cutting, bending, and stamping. The production of sheets requires precise control of thickness and surface quality, so after rolling, they are often subjected to additional processing, such as polishing or anodizing. To create complex parts, various methods of processing titanium and its alloys are used. These can include mechanical milling, turning, grinding, as well as modern technologies such as additive manufacturing using laser powder bed fusion. Additive technologies allow for the creation of parts with complex geometries that are impossible to produce with traditional methods. This is especially important for the aviation and medical industries, where lightweight, strong, and precise components are required. Furthermore, to enhance their performance characteristics, titanium products can undergo heat treatment, annealing, quenching, or aging. These processes change the internal structure of the metal, improving its strength, hardness, and fatigue resistance. In aviation, titanium is used for 15% of the weight of a modern passenger aircraft, significantly reducing its overall weight and increasing fuel efficiency. In the medical field, about 70% of implants, such as artificial joints and dental prostheses, are made from titanium or its alloys due to their biocompatibility and durability.